So today we're going to talk about text analysis in 3D. And this is loosely based on a course I've been teaching for a number of years at the Digital Humanities Summer Institute taking place every June in Victoria. So I've been teaching a course on 3D visualization for the humanities. So some of the examples I'm going to show you today are going to be copied from that course. Some of the examples are brand new. And the goal of today's presentation is really not to present final workflows. So you will see that these are certainly not the final workflows. There are lots of things missing, but mostly to give you some ideas and to show some demos of how you can go from text to 3Ds, how you can actually link different texts together, how you can visualize these in 3D, and why do you want to visualize these in 3D as opposed to more traditional two-dimensional graph visualizations in the first place. And also I'm going to talk about how to scale this up to much larger networks, with many hundreds of thousands or millions of nodes and connections. And in several places in the presentation, you'll actually see that some things I do not fully solve. So I just leave things as they are without providing a solution. And the reason for this is because I don't really want to focus on the computational aspect of this. So for example, in one example, you will see that when I search for common words between different texts, and I do this in native Python, it's actually quite slow because, well, Python is an interpreted language, but I'm sure you can do it much faster. There must be a library for this. If not, then you can actually code it in compiled language. And if you want to help with this, I can certainly help you with this. But that's not the point of today's presentation. So today we're going to be talking mostly about visualization. And another example we will see that there's a shortcoming is I'll be relying, when I talk about graph visualizations, I'll be relying on Network X library to provide us a layout. And Network X library force-based layouts are actually quite slow when you go to millions of nodes. And right now, I don't have a layout that lets you do that, but you can actually write your own. So if you need any help with this, I'll be more than happy to help you. But let's get started. So let's talk about how you can go from text to 3D scatter plots. So this example was based on a blog post, very old blog post from 2009, but you can still access it. So if I go click on the link, you can read the original article, really interesting article. And what they're trying to do here is they analyze a corpus of nearly 6 million research articles from 2,000 plus journals, primarily in science, technology, and medical fields. And they map the position of each journal in the 500 n-dimensional semantic space. So I'm going to talk about it in a few minutes. And then they calculate so they have 2,000 plus research journals. So each research journal is essentially a dot on this map, right? And then they calculated pairwise distances between these journals in this 500-dimensional semantic space. And then they used only these pairwise distances to convert to position these journals in a two-dimensional space that they can plot directly, in the plane of the screen. So here's a typical plot that you would see when you do this in 2D, right? And then they color these by 23 human-created journal categories. So journals come from science, medicine, etc. And they found an excellent correlation between the groups that were found in these automatic analysis and the human-created journal categories. So I took the same idea and I wrote the code in Python, actually quite a few years ago, and then I tried to visualize the results, but this time not in 2D, but in 3D. And by the way, I forgot to mention the slides and all the code examples I'm going to show you today. They're actually online, so let me paste it again into the chat. So today's slides and scripts can be found in this web address. So this is the page that you can open in your web browser later on. And if you scroll a little bit down, there is the text analysis in 3D. And you can see there is a link to the slides and a zip file containing all the scripts from today's presentation. So a little bit about multidimensional scaling that lets you transition from these multidimensional semantic space to two-dimensional space or to three-dimensional space. So this is, I think, a very nice demo of what multidimensional scaling does. So imagine that you have a bunch of European cities, and then instead of plotting these cities on a map, you write down the geographical coordinates, so latitude and longitude of each city, and then you use these to calculate the pairwise distances between these two cities. So let's say we have 24 cities in this map, and then you're calculating a matrix of pairwise distances, so 24 rows and 24 columns, right? And then you only use this table, these pairwise distances, to try to recreate the map. And of course, the map is not going to be exact because the original coordinates are missing from this table. But you still will have a pretty good layout in the sense that any two cities that are close to each other, so for example, I don't know, Copenhagen and Stockholm, Madrid and Barcelona, they will be close to each other in this recreated two-dimensional map as well, right? And two cities that are far from each other, let's say Rome and I don't know, Dublin, they're going to be further apart. So this technique of using the pairwise distances and taking these from a very high dimensional space into a low dimensional space that we can visualize is called multidimensional scaling. So there are various implementations of multidimensional scaling algorithm you can find in Python. The one I really like comes from the scikit-learn library, and this is the one I'm going to be using in this example. So for the texts themselves, I take the following 6 texts. So I take 4 classical English literature pieces. So two novels by Herbert Wells, The Time Machine and The War of the World. So all these texts are public domain, by the way. And then early 19th century, so Charles Dickens' Oliver Twist, late 19th century Adventure of Huckleberry Finn by Mark Twain. And then I decided also to take something very, very different. So my own background is in astrophysics. So there is an astrophysical paper from 2009 that I particularly like. So I just stripped this paper of all the graphics, figures, and formula, and just use the text just to show how different the vocabulary in this paper is from the more classical English language texts. And also I took a novel by Fyodor Dostoevsky in Russian, the Brothers Karamazov, and put that into the same analysis as well. So what we're going to be doing is from each of these texts, we're going to be taking 30 longest paragraphs. So 30 longest paragraphs times 6 texts, that means 180 paragraphs in total. And then we'll be analyzing relative word frequencies and try to visualize the differences between these vocabularies in 3D. So this is the algorithm. So from each of the texts, so 6 texts, we pick up 30 longest paragraphs. So we end up with 180 paragraphs. Then we do some processing. We convert line breaks and dashes to spaces. We remove punctuation. We remove common words like articles and prepositions. And then we count words across all paragraphs and remove words that appear only once across all texts. Then we build a global dictionary for all, actually not 5, but 6 texts. A global dictionary for all 6 texts, and it's going to be combining words from English and Russian. So it's going to be a fairly large dictionary with 11,000 plus words. So we'll be working in this 11,000 plus multidimensional phase space. And then we vectorize, so each of the 180 paragraphs, we're going to vectorize them in this multidimensional semantic space. And then we'll normalize each vector to the number of words in this paragraph because we'll be counting relative word frequencies, right? So for example, if a paragraph is very long, then we're going to normalize the word counts in this paragraph to the actual size of the paragraph. And then we calculate the pairwise distances between all 180 paragraphs. So we end up with a 180 rows, 180 columns matrix. And then we use this matrix to recreate the positions of these 180 paragraphs. So you'll see 180 dots once we visualize them in this in the three-dimensional space. So instead of 2D, I'll be using 3D, and then I'll be arguing that visualizing these things in 3D, especially when you connect them and when you go to larger problems, can actually have some advantages over 2 spatial dimensions. So we take these points in 3D, we store them as VTK points. So VTK stands for Visualization Toolkit Library, and it's a very popular library for scientific visualization. So if you come from digital humanities, you might have not heard about VTK, but it's a fantastic library that's been around for more than 30 years now for computer graphics and scientific visualization. And so it provides various formats for storing multidimensional data. So in this case, we're just storing points as points using this VTK library in 3-dimensional space. And then we take this VTK file and we'll load it into Paraview, which is an open source scientific visualization package. Again, I teach Paraview quite a lot, but if you come from digital humanities, you might have not heard about Paraview, but I'm going to show you some demos where I load the data and explore these graphics in real time. All right, so here's the code. The code is stored in the file semantic mapping 1.py. Let's take a look at the actual code. So let me open the code in Emacs, a text editor. And here is the entire code. So you'll see that it's very easy to understand what's going on. So let's just go through this line by line. So here we are loading various libraries, as I mentioned, for multidimensional scaling by using this module manifold from the scikit-learn library, even though we're not doing any machine learning. And then I'm reading the data. So I'm reading these 6 texts, and just to show you what the text looks like. So for example, let me actually make it a little bit bigger. Here is the time machine. So that's the entire, public domain text, right? I downloaded from, actually I forgot, from Project Gutenberg. So here's the text. Here's the text in, let's see, Brothers Karamazov's in Russian, as you can see, right? So we'll be reading these texts, and from each text we'll be loading 30 paragraphs. So the actual number of paragraphs is going to be variable. Is going to be sized in the stored in this variable in this list size. There's going to list the number of paragraphs actually read from each text. And why do I have these different variable sizes? Because if we try to increase number of paragraphs, eventually you reach the limit of the text. So some texts are shorter, like this astrophysics paper, and then you might not read let's say 100 or 1,000 paragraphs. It could be actually a shorter number than that. And then we also have these tags. So these tags will be used in visualization. So for each of the 6 tags, we store an author tag, right? So we're going to be tagging authors by this integer number, as well as we also store a novel per author. And the reason I have this variable is to distinguish, when we visualize these texts, to distinguish between the 2 works by Herbert Wells, so Time Machine and The War of the Worlds. So we read the text, and then we do some basic processing, so convert line breaks and dashes to spaces, remove punctuation, and then we tokenize the words. So here we remove common words and then calculate a dictionary, right? And then remove words that appear only once across all paragraphs. So eventually we build a global dictionary with 11,000 words in 2 languages. And then we calculate a sparse vector. So actually, let me show what it looks like. So this sparse vector is a list of length 180. So each element in this sparse vector is going to be represent a paragraph. So we're analyzing 180 paragraphs. Let me actually run this inside the terminal. So I'm going to say Python -i semantic mapping 1. And the reason I'm using -i is because I want to run this in a Python shell, and then I will be doing things interactively in the shell, right? So here I'm running the code. Well, it's going to take a few seconds. So it's reading the data. Now it built this dictionary with 11,000 words, as you can see. And so what I want to show you is what these variables look like. So we have the corpus variable, which is just a list of 180 paragraphs, right? So for each paragraph, so for example, for the very first paragraph, what it looks like is this compressed list of tokens. So each token, so these are the IDs. So first number in each tuple is an ID of a word in a dictionary, and then the second number is how often how often that word can be found in these particular paragraphs. So for example, we have 11,000 plus words. So you can see here in the very first paragraph, we're looking just at the beginning of our vocabulary. Whereas if I look at the very last paragraph, it's going to be towards the end, 10,000, 11,000, right? So these are the IDs of individual words in our vocabulary, and then these are the word counts, right? So here we have a compressed, or sparse representation. And then we take the sparse representation and convert it to full vectors. So full vectors is a NumPy array, which has also 180 rows. So if I do full corpus and inquire about the shape of this guy, it's going to have 180 rows. So each row representing a paragraph from our original text, and then the length, so the number of columns, or the length of each row, is going to be the number of words in the number of words in this global dictionary, right? So if I show what it looks like, so for example, for the very first paragraph is going to be 11,000 long array, which here we have the word counts. But the reason I'm going from this sparse representation you saw in the previous variable to these full vectors is because these full vectors are going to position each paragraph in our multidimensional 11,000 dimensional semantic space. So if this is still not clear, I'm going to give you a very simple example. So let's say we have a couple of paragraphs in the first paragraph, we just have the word hello. In the second paragraph, we have the words hi there, right? So 2 paragraphs. And then we build a global dictionary of these. So there are 3 words, hello, hi, and there, right? And then we have a 3-dimensional, so 3 words in total. We have 3-dimensional space. And in this 3-dimensional space, we position these 2 paragraphs. So the first one is going to have coordinates 1, 0, 0. The second one is going to have coordinates 0, 1, and 1. So based on the word frequency, right? So here we're doing essentially the same, but just for a much larger problem. So 180 paragraphs, 180 points, and 11,000 plus words. So then we normalize each vector to the total number of words, or to the size of each paragraph, right? So here, number of words per, well, a document here is a paragraph. So number of words per paragraph. And then we use that to compute the distance from pairwise distances between each of the 180 paragraphs. So this is done via this call from the I forgot from which library, but anyway, so here we're calculating pairwise distances, and then we're using multidimensional scaling to actually project these to 3D, right? And then finally, I write all this, so I print the coordinates. So when I ran the code, you saw a lot of numbers here. Actually, let me run the code once again. So here I run the code, and all these numbers are just the X, Y, and Z coordinates of the 180 paragraphs that I'm going to visualize with Paraview in 3D, right? And then I write this as a VTK file. So this VTK file, this function, I also provided in the zip download that you can find at the link. So this function, let me actually open it. It comes from a file nodes-and-edges.py. So here's the file, and what it does, it stores my node coordinates and a few other things as well. So these things are optional. The only required argument is a list of, an array of node coordinates. So each one of them is going to be X, Y, and Z, right, in 3D. And then optionally, you can have other arguments. So when we look at graphs, we'll be using the same function, right, nodes edges, to store the connections or the edges in our graph, as well as you can have up to 2 attributes. So I call them scalar. So scalar is a list of attributes. So basically, you can have a variable associated with each of the nodes. And then when you load this variable into Paraview, you want to know the name of this variable, let's say an author or novel per author or something like this. So this is going to be stored in the list of scalars called name. And then power is used for scaling attributes. So the idea here is that you might want to scale the size of each point with the scalar variable, or you might want to scale the volume of each point with the scalar variable, right? So depending on which approach you choose, you'll set power to the 1 or 1/3 or anything in between, right? It's just a continuous variable. And then you can also optionally label nodes. And then when you save the file, so here's going to be the file name, right? Test.either VTP or .vtu. So you can save these in one of the 2 formats. By default, it's going to be saved as VTK polygonal data format. And actually, all examples I'm going to show you today will be using just that format by default. But if you want, for some reason, you can also switch to an unstructured mesh, unstructured grid format, and that should work for all examples as well, right? And so here, and then we just write the data. So I won't go through this code into a file that you provide right here. There's a question in the chat. Can you elaborate more on why did you choose this type of word embedding and not word-vec, for example? Yeah, so I looked at a bunch of things, and I can't remember my reasoning, but I don't know, it just worked, and it was pretty fast. So yeah, I remember that I played with a few different approaches, and this one just worked without any problem. So, but I don't know if word2vec will be faster or not, so I will have to try because I just don't remember. So yeah. All right. So let's run our code. Well, actually, here we ran the code already. It wrote into a file text.vtp. So if I look into text.vtp, you will see that this file is very small, so it's only 5 kilobytes. So let me open Paraview. Actually, I'm going to open Paraview 5.12, which is the most recent version. So Paraview 5.12 is the development version. So you see, it's release candidate 1, but I find that it actually fairly stable. So, I mean, alternatively, I can use the previous stable version 5.11. So here I'm going to go to File, Open, go into my current directory. And then from this directory, I'm going to load the file text.vtp. So here's the file. I load it. And nothing happens here visually because what I'm loading is just a set of points, which are infinitely small, right? So if you go to information panel, you can inspect your data set. You can see there are 180 points and there are no cells. So no cells basically means there are no connections. So these points just freely floating points. They don't form any cells yet. So to visualize points, what you want to do is you want to apply a glyph filter that will place, let's say, a sphere on top of each object. So if you do this, you will see a bunch of points. So we know that there should be 180 points. So right here, right, we have 180 paragraphs, 180 points. And if you count these guys, you'll find that it's a small number. And the reason for this is because in the properties of the glyph, there is a setting that tells you how you want to place these glyphs, and I want to place them in all points. So I'm going to place them in all points. And then these glyphs are represented by, these polygonal spheres. And I want to increase the resolution of this each sphere. So I'm going to make them higher resolution. So 30 by 30. So now we have much nicer round spheres. And then I'm going to size each sphere according to a variable novel by author. So in the scale array, in the properties of the glyph filter, I have a novel by author. So I'm going to scale by that, apply. And I guess this is probably a little bit too large. So I'm going to scale it down a little bit, maybe just make it a little bit bigger like this, all right? And then I'm going to color these 180 paragraphs by the author. So now, Paraview could be buggy, right? So sometimes when you create some complex workflows, sometimes it crashes. So to protect ourselves from this, what I'm going to do is I'm going to go to File and then Save State, and I'm going to save my visualization as a Paraview file. So I'm going to call it text.py. And so you're going to see that I'll show you how you can reconstruct your visualization from the state. And this is very useful to know whenever you work with Paraview, simply because, well, if it crashes, it'll be very, very sad if you lose all your work. So I'm going to save it as a Python file in current directory, text.py, and then just accept the default settings. And then if I, let's say, reset Paraview, I can always go to File, Load State, and then go to this Python state file text.py, and here's my visualization, right? So I didn't lose anything. Alternatively, if you like command line, you can actually load Paraview this way. So you can start it from the command line if you're comfortable with typing commands, and then you can say, I'm going to load data from the file text.py. Well, not data, but I recreate the state from this file, and as you can see, it automatically restarts, recreates your visualization. And now I'm going to color these according to the text. So, oops, let me go to my paragraphs. Oh, by the way, here I also have a plot. I thought it would be interesting to see it, what this normalized word count looks like. So here, imagine you're looking at the full corpus, normalized full corpus variable, where on the vertical axis you have 180 paragraphs, and then on the horizontal axis you have 11,000 words. So I couldn't, plot all 11,000 words just because, the screen is not big enough, but I compress them by a factor of 20 into 500 plus bins. And this is, what it looks like. So essentially see that here you have two languages, right? You have English text, and then you have Dostoevsky in Russian, and there is no overlap between them. And so some words are actually, fairly common. So you have some vertical strips, and some words, you don't see very often. Anyway, so in our visualization, we're going to color these by switching to categorical colors. And then you will see it'll be actually very useful because you have only several distinct colors. So we're going to color Herbert Wells in blue. The works by Herbert Wells in blue. So in Paraview, I'm going to go into Edit Color Map, and I'm going to click Interpret Values as Categories. So now I have these 5 distinct colors. So I'm going to say Herbert Wells is going to be author 1, and it's going to be displayed in blue. So let's say this bright blue color. That's Herbert Wells. Then second one, Charles Dickens, is going to be in red. So Charles Dickens in red. Then we're going to have Mark Twain in green. So that's Mark Twain. Then the astrophysics paper is going to be, let's choose cyan color for it. So like this one. So that's the Astra paper. And then Dostoevsky is in yellow. All right, great. So now you can see the results, and things are quite interesting here. So you can see that there are the authors use quite distinct vocabularies, right? And you can see that, for example, if you look at actually, let me save this just in case things crash. So I'm going to save state as a Python file, and then text.py, just overwrite that. And so you can see that if you look at the works by Herbert Wells, they are in blue color, well, darker blue color. And you can see that the Time Machine and the War of the Worlds actually have very similar vocabularies, right? So these, small and large blue spheres, they actually appear to occupy the same region of space, which makes sense. So these were created by the same author. So Mark Twain, for example, has a substantially different vocabulary. Charles Dickens has a substantially different vocabulary. So you can actually see it, as you look at the position of these paragraphs. And then if you look at the astrophysics paper, so it is definitely quite different, right? So it sees on the periphery, right? So very different vocabulary. And then obviously, if you look at a text in a different language, so in this case, Dostoevsky in actually, I forgot to say Fyodor Dostoevsky. So let's actually put it here. So Fyodor Dostoevsky, like this, and then let's just save it, save state. So as a Python file, text.py, yes. All right, so as you can see, the works in Russian are actually very, very different here, and that would make sense because, the vocabulary is completely different, so there's no overlap between the English language text and the Russian language text in this mapping, which makes sense. All right, so are there any questions at this point? Are there other questions? So let's make this a little bit more complicated. Let's also add the four Gospels in ancient Greek. So these actually have, I talk about these in my DHSI course. So I actually do some analysis of the four Gospels and the difference between them. But here I just load the four texts in ancient Greek and apply exactly the same analysis to them. So the code to do that is semantic mapping to .py. So let me actually show the text in ancient Greek. So for example, the Gospel from John, this is Greek, so you can see. And let me run Python semantic mapping to py. So now we're analyzing text in three languages, Russian, English, and Greek. So here we constructed a global dictionary, let's see, with almost 16,000 words, right? And then the result went into a file multilingual.vtp. So here I'm gonna start Paraview. I just killed Paraview a few seconds ago, so I'm going to restart Paraview. I'm going to recreate my previous visualization, right? So I'm going to load the Python file. Right here is my previous visualization. And then I'm going to say, apply the same visualization to my new file, multilingual.vtp. So here I'm going to click on the file. I'm going to say reload files. And then here I'm going to say find new files. So for a new file, let's actually, no, it's refusing to give me, I was hoping that it will give me a dialog, and it's refusing to give me a dialog. Okay, well, that's not a problem. What we can do is I can actually open the Python script, so text.py for the state, and then there was a file where I was reading from text.vtp, and now I'll just tell it, instead of text.vtp, please read when you recreate the state from the file multilingual.vtp, let's see, in both places. Yeah. And then here we have multilingual.vtp as well. All right, so, and let me go to Paraview and then reload that state file again. So I'm looking at a Python file, text.py, and now we're actually loading more text. So if you examine the data, you'll see that instead of 180 paragraphs, we have 269 paragraphs, right? 269 paragraphs. And the author variable, the author variable goes from 1 to 6. So 6 corresponds to the Gospels in Greek. And let me actually color them by, let's apply edit color map, click on the glyphs, edit color map, and then I'm gonna say add a new value. So display the Greek text in orange color. And then I'm going to say Gospels like this for the value equal to 6. So the value of author equal to 6, right? And so here you can see, right? So now we have text in 3 languages. And as you can see, the text in Greek are definitely very different, have a very different vocabulary from the English and the Russian texts, right? Okay, well, all this is good, but how do we explore the connections between these texts? So let's jump to graphs. Let's start talking about 3D graphs. So let's see if we want to connect these paragraphs in some way. So how we can do that? Well, the first question is how can we actually visualize 3D graphs or 3D networks in Paraview? So a number of years ago, when I first started looking into this topic, I looked at the existing two-dimensional visualization packages. So Gephi and Cityscape are very popular. But the problem is that they only work in 2D, right? So that let visualize networks or graphs in 2D. So how do we try to visualize these graphs in 3D? And another question is, do we really want to? So I would argue that there are actually some advantages to visualizing graphs, especially large graphs in 3D. Well, there are 2 advantages. One is you can visualize much larger graphs than in 2D. So if a 2D plot becomes very crowded, you can actually rotate it in 3D and see, clusters hidden beside other clusters, and that way you can actually visualize a much number of distinct nodes and connections. And another advantage to 3D visualization is that sometimes it's just very difficult to make things out when they're very crowded in 2D. So again, with rotation and zooming in and zooming out in 3D, you can actually display a lot more information, and you can make out those clusters much more easily. So I was looking for an open source package that will let you visualize graphs in 3D. And ideally, it should work across platforms, so not just in Windows, but in Linux, Mac, everywhere. And I had trouble actually finding such a package because most of these were either short-lived research projects that somebody created 5-10 years ago, and then they have not been updated in many years. They were Windows only, so I could not run them on my Mac. Some of them are JavaScript. Quite a lot of tools are JavaScript based, so JavaScript is fine, but the problem is that then you actually have to code your visualization in JavaScript, and there's a steep learning curve. So I normally don't program in JavaScript. I'm much more used to languages like Python, or some of these tools are commercial. So there's one promising package that I actually discovered recently, which is called Gravis. It has not been updated in 2 years, but it's actually a Python package, and it lets you construct 3-dimensional graphs that are interactive. So if I'm going to show you an example. So if I go to this page and then go to here, so here you can see an example of a 3-dimensional graph, and there's actually a live force layout, right? So I can drag nodes, and the whole graph reacts. And so this is very interesting, and I'm actually planning to do a webinar on this package next term. But here I'm using a different approach. So here, instead of looking at a dedicated graph visualization tool, I actually say, well, we can try to visualize these graphs in Paraview. So one thing is that if we want to apply any sort of a force layout, then we have to use a specialized package for processing graphs. So I'll be using a very popular package called NetworkX that lets you create graphs, so nodes and edges, and also apply a layout, let's say a force layout or a non-force layout to these graphs, and then store these graphs as a bunch of nodes and edges in a VDK file using exactly the same routine I showed you before, and then visualize this in Paraview. And one of the advantages, there are certain disadvantages, is that we're not using a dedicated graph visualization tools, right? So you cannot do things like you do here, for example, where you see the graph and you can drag a node, and then the whole thing just reacts according to some layout rules, right? So that won't be able to do in Paraview. But one big advantage is that Paraview has been created for visualizing very large data sets. So it's actually it can scale to much bigger networks. So the existing tools, I'm going to show you examples, can scale easily to hundred thousands of nodes and millions of connections. And actually, you can scale it. I know how to do it. You can scale it to billions of nodes and tens of billions of connections. So if you're interested, if you have such a problem, let me know. I'll be more than happy to help you visualize it in Paraview. But so it's not terribly interactive. It's a little bit interactive, but in a different way. So you'll see how. And then so we store this as a VDK file, and then we play with that data in Paraview. So the package we're going to be using is called NetworkX. It's a Python package, and it provides a number of built-in graphs. So actually, let me open the Python shell. So how are we doing time-wise? Okay, so we have 20 minutes left. So let me open Python, and let me import NetworkX as an X. So I'm going to say import NetworkX as an X. And then if you look at what's available inside the Next library, it's a huge list of various functions and attributes, many hundreds of names in that namespace. So what we can do is we can say, actually, I cannot copy from here. So okay, well, if you run this code, if I were to paste it in here, it will give me a list of 139 built-in graph types. So there are lots of graph types like random graph or bipartite graph, etc., that you can just create by calling a function from NetworkX. And in addition to graphs, there are also layouts. So a layout is basically a collection of rules that you apply to a graph, and that let you position these graphs according to this rule. So most famous layouts are Force-B layouts. So there are a couple of Force-B layouts, I guess Spring and Spectral, inside NetworkX. So the idea of Force-B layouts is that if you have any two nodes that are connected, they will attract each other, right? And then non-linked nodes, so nodes that are not connected, will be pushed apart, right? So this way, by modifying the strength of this connection, you can actually reposition these graphs very easily. So depending on your Spring strength parameter. And so you can create these graphs very easily by hand. So for example, you can say, let's create a random graph. And here we're creating a random graph with 10 nodes and 50 edges. Then we're applying a shell layout to it. So shell layout will basically position these nodes in a shell. So it's not a force-based layout. So this layout can scale to very large number of nodes, to millions of nodes easily. But the problem is it's not particularly meaningful because it doesn't take advantage of the connections between these nodes. So I mean, in reality, most of the time you probably want to apply force-based layouts. So here's an example of a graph where we simply use a random graph and then a random layout. So we have 100 nodes and then 500 edges, and then we return a dictionary of positions. So this layout function returns a dictionary of positions. Then it can use to create a list of positions X, Y, Z that you feed into this right node edges function that we used before. But this time, in addition to supplying the coordinates of the nodes, you also supply the edges, right? And the edges is returned by this graph function, right? So let me run this and then load it into Paraview and show how you can visualize this. So I'm going to run a random graph 1.py. So I'm going to say Python and then random graph 1py. So this is going to create a file network.vtp. So I'm going to go to Paraview, clear my current visualization, and open the file inside Paraview. So I'm looking at the file network.vtp. And so here we see a graph, right? And then we know that, so this graph, if we go to inspect properties, we'll see that here we have 100 nodes and 500 cells, so 500 connections between the points. So we can put a glyph, let's say a spherical glyph on top of each, oops, sorry, not a line, but a spherical glyph on top of each point, right, like this. Make it, let's say, high resolution, like this. And then if you want to apply, let's say, we can color them by a variable called degree. So this variable called degree is actually in my code. And what it does is returned by this line, but it's actually, the degree measure is returned by the function that I used to construct the graph. And what it is, it's simply a measure of the number of connections for each node. So the nodes that have, are red in color, well, let's actually scale them according to the number of connections. So for the scale array, we're going to use degree. And let's scale them in according to the number of connections, right? So you can see that nodes that are well connected, they are in red and they're bigger, and vice versa. So let's actually apply another filter to our network called tube. And that way I can actually play with the properties of the edges, right? So right now you see that these are my edges. And then let me scale the radius. So let me make it not as big like this. I can also change the opacity. So, for bigger networks, you probably want to play with opacity so that, these edges don't dominate your network. And then, all this is fully interactive in the sense that you can rotate it. You can spin, you can apply various filters, but you cannot drag because this is not a graph visualization tool, so you cannot take a node and drag it, right? Because dragging will just rotate it in 3D. And also we can color the the edges, the connections by our degree variable, right? So here we have coloring, all right? And then if you want to save this as an image, you go to File, Save Screenshot, and then choose, the resolution, the file format, and so on. So if you want to apply a force layout to this, there is a code random graph 2py. So the only difference between random graph 1 and random graph 2 is that instead of applying a random layout, I'm applying a spring layout. So in fact, let's just do this. Let's run the second code. So I'm going to run random graph 2py. Is going to write into the same file network.vtp, and then I'm going to reload the file. So I'm going to say, now instead of looking at the random layout, let's reload the data file. So now we have a force-based layout, right? So you now see that nodes that have a lot of connections, that have a high degree variable, they appear closer to the center, right? Whereas on the periphery, on the outside, you have all nodes with a few connections, so small nodes and the ones that are primarily in blue color. So that's a force-based layout. Anyway, so let's go back to our problem with adding graphs to text visualizations. So one thing we could do to create connections between the paragraphs. So here we are back to the problem with six original texts and 180 paragraphs, is we can simply use the distance measurement. Remember that when we're doing multidimensional scaling, before multidimensional scaling, we're computing a 180 by 180 matrix, pairwise distances between all paragraphs, right? So we can actually use these distances as a measure of connection or similarity in vocabulary between any two paragraphs. So in fact, if I look at the code, so I'm going to load semantic mapping 3.py code, make it a little bit bigger. And then here where I compute the distances, right? So here I'm computing the distances, pairwise distances, before applying the multidimensional scaling algorithm. So here I compute the distances, and then I'm saying if a distance is between any two paragraphs, so 180 paragraphs, 180 points here, is smaller than 0.014, then create an edge connecting those two paragraphs I and J, right? And then write all those edges into VDK file. So here is what it looks like. Let me actually load it into Paraview and already created a workflow. So it's called on my laptop workflow 3.py. So let me actually do this very quickly like this. I'm going to say Paraview and then load the state file, workflow 3.py to quickly show you what it looks like when you go through, set all the properties. And so here's the visualization that we get in the end, right? So you see that all nodes that are closer than 0.14, in some arbitrary units, dimensionless units in this multidimensional phase space are going to be connected, and nodes that are further apart in the space are going to be not connected. So the problem with this visualization, so it's a nice graph visualization, but the problem here is that here we have text in English, and here we have paragraphs in Russian from Dostoevsky, and they're still connected, right? So it just happens that when we're calculating distances, some of the paragraphs in Russian and English text happen to be closer than 0.14. And if you want to play with this parameter, you certainly can. So you can change this number to a smaller number, but that actually will not give you a meaningful measure. So the problem is that this measure is completely arbitrary, right? So it gives us this nice positioning according to the rules of multidimensional scaling, but it doesn't really give us proper connections in the sense that it doesn't show similarities in vocabulary between any two texts. So instead of one thing that I forgot to mention, you can also apply. So in this case, the positioning is done according to the output from the multidimensional scaling, right? So right here, all positions of individual nodes is done from, is coming from the multidimensional scaling. So connections come from, this measure of distance. But we can also apply a force-based layout to these nodes. So in this case, connections will still be coming from these these arbitrary distance measurements, but then the positioning is going to be done according to a force layout rule. So here I have semantic mapping for pi code that does exactly that. So here I'm applying a force-based layout, so spring layout, where I'm taking my network. Here I have a certain parameter, so it's string strength in this layout, and then outputting these to three-dimensional positions, right? So in 3D. And here is, you see in output, so here are two examples of, for two different string strength. So the key parameter. So here it's smaller, right? So here we don't have as tight connection between the small distance between the connected nodes, right? And here we have much tighter connection between the connected nodes. But as I said, the problem in all these visualizations is that the text in Russian and in English are still linked together, which is probably not what you want to see, right? So instead of using distance as a measure for connectivity for creating edges, what we can do is we can simply connect any two paragraphs that have at least 5 words in common. And in Python, it's actually really, really easy to do that. So here's the code, semantic mapping for pi. What I'm going to do is I'm going to simply run it, load it into the Python shell. And then I'm going to look at, so now it's computing these distances. So here you see the progress bar. And so the problem with this implementation is that it's done in native Python, right? So I'm sure you can probably find libraries that will do it for you much quicker. Python libraries written in compiled languages like C. But here I did just in native Python, so it takes something like 20 seconds. The thing that I want to show you is in Python, the reason why I did it very quickly in Python is because it's very, very easy to do. So here we have the full corpus. So it has 180 paragraphs, and then each paragraph is, has these measurements for the frequency of 11,000 words. So let me take one of these guys. Let's say this guy, right? So this is one of the paragraphs. And I'm going to say this is going to be equal to, let's say, D1. And then let's take D2 in another paragraph. So let's say paragraph number, I don't know, 10. And you can actually analyze find common words between these two paragraphs very, very easily in Python. So here's what D1 looks like, right? So these are, this is word number 1, word number 2, word number 3, and these are, count measurements. So how often do you see this particular word in the paragraph? So we can see D1 is not equal to 0, right? So these give us essentially a mask saying that whenever it is true that word is present in a paragraph. So this word is present, this word is present, this word is not present, and we can actually take that and then multiply it by the same measurement for the second paragraph. So we can say D2 is not equal to 0. And when you do this, it will be true only for those words that appear in both paragraphs, right? So some of them will be true. And to count them, all you need to do is just pass that into some function. So in this case, between paragraphs 0 and 10, it actually found 26 common words. So here I'm saying that if the number of common words between these two paragraphs, D1, D2, is bigger than 5, go through all pairs, then create an edge. And then, as I said, this is fairly slow for 180 paragraphs, 11,000 words. It takes some like 20 seconds on my computer to do in Python. You can do it much quicker in a compiled language. But then let me show you an example. So it's Paraview workflow 5. So here is the output of all this analysis. And what you can see is that now there are no connections between the English text, and the Russian text. There are Russian paragraphs, right? So now they are totally unrelated to each other, which is exactly what you want to see. But another problem with this is, the properties of these two sets of text are entirely different from each other. So here we have, very loose connection, a very, spread out network, whereas in the second case, we have a very tight network, shown in this sphere. And I can do things like this, right? I can only see, only show the nodes, right? And here you see that, all these nodes are very, very tightly connected. So of course you can apply different rules to these two different layouts to do these two different sets or two different languages. So in this code, semantic mapping 6.py, I don't have time to go through all the details, but here essentially what I'm doing is I apply the separate layouts, so Spring layout to the first 5 tags, and then I apply a separate layout to Dostoevsky, and then I use completely different strength of parameters for the layout for the Spring strength, right? And then you have a much better visualization, right? So also you can assign completely different visuals to each graph, right? And there are two ways to do that. So either you can load everything through a single file and then apply Paraview filters. So again, I won't show you the demo now because it will take more than a few minutes. And then apply two filters, so you can create two different objects inside Paraview, and then we'll apply completely different visuals, set of properties to each network, right? Or you can just save them into separate files. So the example of separate files is given in this code that is part of the zip download. So let me actually show just an example of the output of this code. So here we apply completely different layouts to the two languages and also completely different visuals. So as you can see, there are two sets of objects in the pipeline browser. So here we have the English text, and then here we have the Russian text, right? And then totally different layouts, totally different visuals, and very easy to do in Paraview. So in this case, I'm just reading these from two different sets, from two different files. So finally, I want to talk about scaling this up. Oh, one thing that I probably should mention is another thing that you might want to use the third dimension for is to encode a third variable. So in this example, which is, let me actually run it quickly. So in this example, I apply a flat layout. So I apply a Spring, so FOSS-B layout, but I do it in 2D as opposed to 3D, right? So it creates, these two-dimensional structures. And then I use the third variable to encode the year of publication. So for example, the astrophysics paper was published in 2009, right? So it appears on top of, the rest. The first one is Charles Dickens, and then Herbert Wells and Mark Twain, so late 19th century, are sitting in between. So the point here is that you can actually use the third variable to encode, another the third dimension to encode another attribute, which could be the year of publication or number of protagonists, or any of those things, right? So this is another reason that why you might want to use the visualization in 3D. And so when you try to scale this up to much higher number of nodes and edges, you will find that the limiting factor is actually not visualization. So visualization-wise, Paraview can very easily display, millions or tens of millions or hundreds of millions of nodes and edges. The limiting factor is actually the force-based layout from Network X library, right? So those layouts become very slow when it comes to doing this for millions of nodes, and you can see why, because the force-based layouts they go through all pairs of nodes and then position them according to the connection strength between those two nodes. And of course, for millions of nodes squared, this will be a very expensive algorithm. So just to demo this, the scaling with an artificial problem. So here I have a graph that's called Dolgov-Mendes graph. That is actually a fractal graph, and the way you construct it, you start with two nodes connected by an edge, and then to go to the next generation graph, you go through all edges, and then for every edge you create a new node, and then you connect that node to the ends of to the end nodes of that original edge, right? So here from one line we'll go to a triangle, and then for each of these edges you create a new node, and so on. And another way you can go from the previous generation to the new generation is that in the new generation graph, the previous generation graph always appears 3 times, right? So here you have a triangle, and then this triangle you see 3 times. But the point is that using this algorithm, and it's one of the functions, this graph is one of the functions inside Network X library, you can actually create very large graphs, artificially very quickly. So here's the function that does it. And then you can run it on your own computer, and then you can visualize it. So here is what the seventh dimensional graph looks like. And actually, let me load it very quickly. So I'm gonna run Python dgm.py, create a seventh generation graph, and it's gonna have 1,000 nodes and 2,000 edges. So here it wrote into network 9.vtp. Actually, I don't remember. Let's see. I don't have a workflow for that, so let's actually load it into Paraview from scratch. So Paraview 12. So I'm just going to load a file called network 9.vtp. So the file is network 9.vtp, and here's what my network looks like. So I can position, place graphs here, etc. So let's say a sphere on top of each point, right? I can rescale them. Let's say make them smaller, but you get the idea, right? So here we have a nice seventh generation graph, and this can scale to much bigger problem sizes. But the problem is layouts. So layouts are very difficult to compute. So here I ran a couple of visualizations. So I created a 10th generation DGM graph, which has almost 30,000 nodes and almost 60,000 edges, and very easy to visualize in Paraview. The problem is applying a layout. So if you apply a traditional Spring layout, it actually takes 15 minutes. So generating the graph takes only a fraction of a second, but applying a Spring layout takes 15 minutes on my laptop. So there is another layout which is also force-based called spectral layout in Network X that is faster. So I actually here apply it to an 11th generation graph, and then it takes 2 minutes to compute it. So let me actually show one of these guys. So I'm going to load Network 91 into Paraview, what it looks like for 60,000 edges. So let's say Paraview 12. And then I'm going to open a network 91 file. Right here. And here's we have a graph with 30,000 nodes and then 60,000 edges. As you can see, it's completely interactive, so I can easily, play with it, rotate it in 3D, and everything is very responsive. So you can scale it to millions of nodes, but then, as I said, the problem is layouts, right? So the layouts become very slow. So here, for example, I created a 15th generation DGM graph, which has millions of nodes, millions of edges. It takes just a few seconds to visualize a frame with this number of nodes and edges. In Paraview, the problem is the layout. So I can only visualize it using the random layout, which is kind of meaningful because it just places everything randomly and then just fill a unique cube with all nodes and edges. It doesn't look pretty. There's no fast, meaningful and pretty force-based layout in Network X, just because it takes a while to position these many nodes. But you can actually create your own layouts in Python. So I didn't do it in this presentation because, well, we don't have time. But you can actually do this fairly easily if you don't use a force-based layout, but use a layout where you position nodes according to some rules, let's say on a grid, right? So for example, there is various attributes associated with each node, and then use this attribute to position these nodes in 3D. And then you can actually do it in Python, and you can write very fast code. As long as you don't use a force-based layout, you should be good. So yeah, I think I'll just stop here. So because we are out of time, but the last two slides show various algorithms that you can use to calculate the properties of networks in Network X library. And there are literally several hundred built-in algorithms, various functions for doing calculations on graphs. So here's an example that calculates centrality and then visualizes centrality measure for each graph. So centrality measure is similar to a degree. So degree measures number of connections. So centrality, what it does, a centrality measure for any node in a graph will be high if that node is connected to other high centrality nodes, right? So in order to compute this measure, you actually have to do it iteratively because you cannot do it only once. You have to, know the connections to other, high centrality nodes. And there's a function in Network X that lets you do this very quickly. Anyway, so I think we're out of time, so I think we'll stop here, and then I will pause for questions.